here, we're going to move next to determine the force vector. Okay? So, as you know that the triangle element, they have 1, 2, 3 sides. Previously, we might apply local force at not 2, not 3, not 1. Okay, but the question here is, sometimes the force is applied on the line, but not on the node. And then how do you do the division of the distributed load on the individual node? Okay? So imagine line 2, 1 is subjected to force or tension in x and y directions. Okay, uniform tension Tx, uniform tension Ty on not 2, 3. So now the idea is we want this distributed force to be lumped to not 2 and not 3. Okay? In this case, not 1 but the opposite of 3 have no share of the traction force simply because of our assumption on interpolation. Okay? So how do you obtain this? Okay? So to obtain the normal force, one very important point is the work done by the force. Let's copy this to the opposite side. Then you'll see it clearly. You can do the division here. Okay, you see that? How do we split up the force? If the force is distributed force. Okay, one way we do is we still use energy method, but we try to find how much is the work done by the distributed force. So then you must find the horizontal force times the horizontal displacement along the line 1, 2. Then you must find how much the work done by the vertical force times the vertical displacement along the line 1, 2. Okay? And then next, the local force on the nodes equivalent force on the nodes can now be obtained by partial differentiation of the work done by the traction with respect to the nodes. Okay? So now if you go and do the partial differentiation, like for example, if you're going to do the partial differentiation of the work done by U1, so the only term that becomes non-zero is del U1 del U1 is 1 times N1. So this gives you integration of N1 times traction force and then integration along the length. Okay, integration along the length. Okay. So this convert to be a line integral. Okay. So this is for force on not 1 in the x direction. How about the force on not 1 in the y direction? You have to do the partial demonstration of the work done with respect to the vertical displacement v1. So the only term that is non-zero is del v1, that is n1, and traction in the y direction and line integral. Likewise, you can do the partial differentiation with respect to the not 2 in the vertical and horizontal direction. Then you're going to obtain the not 2 vertical horizontal force and not 2 vertical force. Okay? So this is the way how you obtain the normal force. Okay? Yeah. I think it's this one is the same. Yeah. But I just want to do the plotting. So how do you do the line integral? The question comes here. Okay? The line integral here, okay, along the two nodes, you're going to see if this is a linear interpolation function. Line integral of the straight function with respect to the straight function, the integral of line integral of the straight function will be equal to half. Okay, because that's the nature of interpolation. It's 0 here, it is 1 at the end. Okay, so this is going to half. Okay, this makes our calculation very simple. Okay, complication comes here if the local force is not a constant. The local traction force is on the bottom side is constant, but on the vertical side is not constant. How will we be able to find the normal force? Okay. So then we need to use the same shape function to interpolate the force. Okay. So as we told you before, you can use what you learned before, do step-by-step partial integrations. Alternatively, okay, you memorize that the shape function for not 1, just the equation for opposite line. You set it to be 0. This is 1 minus x. And passing not 1, 0, and not 1, 2. Okay? 1 minus x. Is it 1? And when x is 0, yes, it's 1. So that's the correct shape function. The other way around is we will be able to find the shape function from 2. You write the equation of the opposite line. This is 2y minus x or x minus 2, 1. But the condition is when you substitute 1, 0 to the shape function, this must be 1. So in the end, it turned out to be x minus 2y is the right one. You don't want it to be negative. Okay, how about the shape function at 3? It's opposite line. This is y equals 0. Okay, at height of 2, you want it to be 1, then this is going to be y equals 0 divided by 2. Okay, so this is y equals 2 shape function. Okay, so in this way, you obtain the shape function. And then how do you find the work done by the uniform distributed force, this is non-uniform but linearly distributed force, you express the x, okay, and y as a straight function, okay? How to write this? Look at the force here. What is Ex? Ex along line 1, 2, okay, is your N1, okay, and then Tx1 plus N2 Tx2. So means your previous multiplications got to, okay, on node 1, 2, no issue, that's fine, but on node 2, 3, then you got to write something different. Yeah, this is not 2, 3. 1, 2 is the bottom one, and I think that's fine. Okay, let me move it to the opposite side. On the not 2, 3, you see you have N2 into x, N3 into x1 for the integration. And then your N2 E2y and N3 E3y. Good thing here is it is a horizontal force, okay? And being 0 at not 2 and being non-zero at not 3, okay? So in this case, you're only left with U2 being 20 pounds and U3 being 40 pounds. Yeah. So that's the way how you handle. Then we come back to our example just now. In this example, yeah, you got to calculate the B matrix. You got to calculate the K matrix. Okay? And you eventually want to find out what is the answer. Okay? So for element 1, the only free nodes is not 3. U3, U3 is non-zero. Then they are associated with these 2 by 2 matrix. And then next, how about the element 2? The only non-zero elements are not 3, 4. Okay? Yeah, so the expression here is quite a tedious one. Okay? And then you sum the forces on node 3 and node 4. For the first element, you have force contribution on node 3. For second element, you have force contribution node 3 and node 4. And you do the sum up. You see your horizontal force on node 3 and node 4. There are zero vertical force. It's going to be equal to this expression. And then next, how to solve this? You solve this by then I can do the solutions. Then if you want, then let's do the solution. Let's see if I can do the solution. Okay, let's do the symbolic definitions of H, L, V, what else? T, A, E, stiffness. And then the stiffness is this expression. What's the symbol? Okay. I think we miss a H. Oh, we also miss a V. What is not defined? E, A. Okay, what else? Let me see here. Oh, this one. Okay, this one is okay. This one incorrect. I think this is the B now. The B is the incorrect. Okay, this is the stiffness matrix. Okay, and then next, let's find the force vector. In this case, we have to define the attraction force. We have to define the force vector. Okay, and then now we define the displacement vector as a force vector. And then A. Okay, let's see. reverse. Top right, reverse. Okay, and 44 and the form vector. Yes. Yeah. That is going to be a very complex expression. Let's simplify it. Okay. Yeah, it's still, yeah, very complex. Okay. So let's see the displacement in the vertical directions. Okay. You can see that they are planary depending on the tensions. Okay. Okay, but my expression here, I got to do the correction here. Okay, my force vector. Okay, you forget to multiply these. So this one got to multiply with the 2 times the thickness times the height, and then so times the area times 1 minus b squared divided by e divided by thickness. For the simplicity, you can remove pH on both sides. Anyway, just do that. Yeah, we need to do the multiplication. Yeah, you can see the actual deformation will be quite complex. Okay, but after all, you will see the effect. The main deformation is along the length direction. You see, okay, sorry. This one I think I got multiplied on the wrong side already. This should be multiplied along the fourth side. Rather than so you can see it is the traction times the area times this meter cube divided by, I think they got to be simplified. This guy not quite right. I think you didn't do the simplification of the H. Yeah. So this is the displacement in the horizontal direction on not 2 and not 3 and 4. Okay, so you can see primarily they are here. Okay. So this is to say, even though you are doing the pull, okay, the expressions is complicated by the Poisson ratio. But if you now go and replace this force by the horizontal, by the number. Okay, this force value shall be very close to the spring model. Okay, but this accounts for the Poisson ratio effect. Poisson ratio effect. Okay, with this then. Then we're done for this. This is a good solution. So the answer here is U3. This is U3. This is U4. And this is U4. Yeah, it's going to be quite a tedious one, so let me try them now. So next week we shall have the NC sessions for this. And then now let's come to the next part of the lecture. For this part, we really come to the modern finite element formulation. Previously, you are using the physical law, you are using the idea of interpolation. Okay, but that kind of method work for structured element. You cannot apply it to general field. Okay, so what here is structured analogy. We use structured analogy, but now next we're moving to isoparametric mapping. Okay? Yeah. What is meant? Previously we are using absolute coordinate x and y. Okay? We are using interpolation for displacement. Okay? But now for odd shape, which is not triangle, which is a quadrilateral shape, you sometimes don't want the coordinate to be expressed in x and y. You want the coordinate to be interpolated as well. So the interpolation here is the previously this is the structural analogy is interpolation of displacement field. Okay, this one, interpolation of displacement field, as well as the interpolation of the coordinate within the element as well. Yeah. So when you say iso means that in both displacement field and the coordinate field. So you might not see this clearly, okay, but you can remember your model, this legged model. So because of the loading, you have displacement, but your rock, okay, is defined using your coordinate x1, y1, x2, y2, and then this one defined using displacement u1, v1. Okay? So previously, because it's straight line, you do need to do interpolation of the coordinate. Okay? But later you see that if I'm having a square, it's easy to do integration. If I'm having a trapezoidal shape, it's difficult to do interpolation. So, yeah. So why not I do the mapping? If I'm going to do the mapping of coordinate. Okay? Mapping your way is what it means in interpolation. Okay, but from one coordinate to another. Okay. So you might not see this very clearly, but I'm going to show you a few examples. Okay, this is just telling you meshing you may want to do coordinate experiment. The more the mesh, the closer to the exact solution. And then the interpolations must fulfill the continuous boundary. Okay, and then completeness is, yeah, you linear interpolation, if you want to make it quadratic, yeah, you can express it, but don't forget that you need a constant value so that you can take account for the rigid body motion. Okay, this is what you interpolate. I think you kind of have a framework already because you have already done the interpolation of the thrust element, beam element. Beam element is naturally a quadratic element. So this is all we have done before. Okay, so this is how you find the interpolation functions. Okay, this is all for the displacement field, for temperature field, for the variable you want to determine. Okay, but we forget to tell you that we're now not just interpolating the displacement field or temperature field, we can also do the mapping of the coordinate. Okay, this is an interpolation in shape function from displacement field. Okay, you already know how you did it. But for the isometric one, we want to do the mapping. Okay. If you have a square one, no need to map xy coordinate is enough. But if you are handling this kind of trapezoidal shape, okay, this one no need mapping. This one might need mapping. Okay? If this is mapped, how do you find the stiffness? The main reason why you do mapping is not for concentric triangle, because for concentric triangle, not so much worry because the integrations, it's just an integration of the area. The B matrix, transpose, D, and multiplication with the B are constant. So you don't worry about that. The only thing that you worry is a variable of space over a non-Cartesian space. Okay? So one example that we can show you that why mapping is important is, take for example, in this case, if this is 1 over x, okay, you can do the integrations of this non-linear one, okay, but you can alternatively do the inverse, okay, then you can make the function, make the curve to be linear. You see, this is 1 over x. I'm going to do the integration from 1 to 2. complex, not too difficult, it's log 2 minus log 1. Okay? That's going to be the area. Why not we do the inverse? If this is the inverse, 1 over x is equal to u. But now the integral has to be changed. I'm not integrating with respect to x. I'm integrating from beta to alpha. Okay? And that's going to be expressed as Jacobian dx du times du. This is a chain rule. Rather than integrating from 1 to 2, I'm integrating from 1 to half. This is u equal 1. Okay? So let me write it out. And this is the chain rule. And in this case, the chain rule, we have to substitute what is del x del u. Okay? X is equal to 1 over u. If the dx du, then it is going to be minus 1 over u squared. By doing the substitution in, okay, you're going to obtain almost the same thing. Okay? From 1 over u. That was the use of the complex expressions, complex function for you to visualize. Okay, another thing that we can continue to expand is if you have a function to be integrated over an area, but that functions have a complex bound. Okay? It's not the integral bound. Then you can try to use the bound, okay, to simplify the expression. In this case, the bound can be defined using u and v coordinate. Then rather than integrating with del dx dy, then you have to integrate over the space of Jacobian times du dv. What is this Jacobian? This Jacobian is it's a chain rule. It is del xy over del uv. And the Jacobian is expressed in the matrix or determinant form, okay, as del x over del u, del x over del v, del y over del u, del y over del v. So what's the meaning here? The meaning is this Jacobian is indeed carried. Okay, let's take an example to show you. If I want to integrate the displacement chain over a quadrilateral over this parallelogram, that integration will be very complex because the bound is so difficult. Okay. If it happens that I'm integrating 1 over this bound, okay? Don't worry about the equation. You only have one bound is 2y minus x equals 0. Another bound is higher by 2v. So how much is the 1 times the area integral? Okay? So if you want to do that, you can define the value to be integrating along the height. This is going to change from a variable b from 0 to variable b to 2b. Okay? So in a way, you can see that my height of area integral can now be made into v. Okay, my u remains the same as x, okay, but my y, I change it to variable b. So my area integral, do you see that? Is going to be the same. 1 times dx dy over the 2 bound is going to be changed to be Jacobian times du times du between the bound of 0 to a, 0 to 2b. Okay. So this gives you a way how you Jacobian del x del u, del x del v, del y del u, del y del v, and you now doing the substitution in, okay? Then you can find the area. This is the direct method in the top. This is the indirect method by Jacobian. By doing the, look at this, del x del u thing. Okay? Look at this Jacobian, del x del u, del x del v. If you now do this determinant, then you can see that how simple the integration. Okay. 好，所以我们现在做这个你的坐标或者是转换，主要的目的就是让你的积分变成比较容易。OK， 就比如说你的平行四边形，空间上乘上1。OK， 你的积分是它的高差，它相对 x。那我的上面的线跟下面的线都是斜线，它只是差一个2离子。那我是不是高差把它转换成像这种方式？这样的一个坐标转换。Okay. You might see this to be very simple coordinate transformation on the grid. But look at this. How do you handle the area? Okay? The coordinate, if you want to do the area integration, it's too complex by Cartesian coordinate. Okay? But rather than using Cartesian coordinate, if you are using radius and angle, your Jacobian will become del x del theta, del x del r, del y del theta, del y del r. This is simply this expression. This is r cosine squared theta sin theta. Then now you can obtain simple expressions by integrating from radius equal to 0 to radius equal to capital R. And these expressions, an integration from 0 into 2 pi, then you are going to find out the area of the square. Okay? Yeah. So if you still don't feel the direct impressions, just look at how variable change was used to calculate your area. If, for example, you might have bought a pie or a cake. You can cut it into 6 or 8 pieces, and then you pad up every one end of the pieces. This will give you the radius, and up length is 2 pi over 8. Okay, and the radius. Okay, then because you have 4 pairs, then you will be able to find out what's the area, and it's approximately pi r squared. Okay, this is how to use the chain of variable to vary. Then next, you can also do the same for the triangle. Okay, imagine you have a triangle of span of A and height of B. Okay, you can do the Jacobian by changing a variable. Okay, rather than integrating from 0 to A and 0 to B, you want to integrate from unit from 0 to 1 and unit from 0 to 1 in the vertical direction. Okay, then let's ask you, Why can't I do integration in terms of A and B? Why I want to do integration from 0 to 1, 0 to another 1? Can you have a sense? Why can't I do integration over the absolute coordinate? Why I have to do integration between 0 to 1? Right? Okay, so if you're going to handle the triangular element like what we did, okay? But now, look at the example here. If you need to do integration to find the B matrix, okay. Are you happy with this? Okay. Are you happy with this stiffness matrix? This stiffness matrix is obtained from the area integral, okay, and multiplying with only the constant matrix, okay. So for linear case, okay, because the stiffness part is independent on the space, okay, then there should not be an issue. But if you happen that you have the polyhedral element when the strain is not constant, then your integration will be very complicated. You want some tools that give you a number, okay, that is easy to integrate. So that's why you need to do the mapping. Integration from 0 to 1 is very simple, it's dimensionless. But integration from 0 to A is dimension, okay? So every time you do that, integrations could be different with respect to the actual length, okay? So in this case, your mapping of Y will be V. V is Y over V, and then X, U is X over A. Even though this is a simple mapping, but it will greatly help your calculation. And some more, there are integrations, dx, dy, and integration to be done over dv, du times the Jacobian will give you the same area. So that's the basis why we need to do this, okay? Yeah. Okay, now let's come to the part. Okay, we previously learned about shape function in terms of coordinate x and y. That is in terms of the absolute coordinate. But now we want to express the shape function in terms of another two coordinate. This is your zeta and zeta and eta. Yeah. So in this case, n1 is zeta, and then this is n2 is eta, and then the n3 is 1 minus another two shape function. Okay, how this coordinate is defined? This coordinate is defined, n1 is the opposite area of the point divided by the whole area. And n2 is the opposite area of n2, not 2, divided by the whole area. So this kind of mapping, what does it do? You can make your x interpolation, okay, coordinate mapping, to be n1x1 plus n2x1, n2x2 plus n. This is n3x3, okay? Yeah. I need to do the correction here. By substitution in the non-dimensionless coordinate, Okay. Then your expression here is your x and y. Okay, can all express in terms of zeta and eta. Okay. And then next, just give you a understanding about this non-dimensional mapping. Okay, how much is your this shape function zeta and eta? Okay, at this point. Okay, so what you do is by taking up the value. Okay, what's the x here? The x here is 3.5. At 3.58 is equal to x3. Okay, plus zeta x13. Zeta x13 is the x in not 3. That's minus the not 1 minus not 3. So it's 1.5 minus 4. And then this one is zeta times x2 3 x2 is 7 minus x3, that is 4. Yep. So by doing this, then you can find how much is your zeta and eta at the north at the point P. Okay. So the isoparametric representation now have x and y all represented in the new coordinate. Likewise, you do so for your u and v, and in short, now you have everything expressed in terms of zeta and eta. Okay, now because you have net the area, you cannot do normal gradient. Okay. So now your expression here. Okay. The left hand side is the coordinate interpolation. The right hand side is displacement interpolation. All in terms of zeta and eta. Okay. In this case, you can do the partial differentiation of del u del x to find the strength. Okay. But you got to, because it's depending on the dimensional coordinate zeta and eta, then you have to do the partial differentiation del u del eta, and then del eta del x, and then this one is del u del zeta del x. Okay. And then likewise, you can do the partial differentiation with respect to y coordinate, that is del u del eta del x, and del u del zeta and del zeta del y. Okay. Okay, but for this, you don't express this del u del x, okay, to be this expression. Why don't you do that? Because del eta del x is implicit, okay? So that's no good, okay? What we want to do is you want to do the explicit expression del u del zeta to be expressed as del x del eta, and then del u del x, and then del y del eta times del u del y. Okay. All this matching is kind of like helping you, okay, to obtain the displacement field with respect to the net coordinate. Okay? And it can be related to the actual strain by pre-multiplication in the Jacobian matrix. Okay? 所以这个有点难，主要就是说你积分的需求，你不想去积一下子三角形，一下子梯形，或者一个是正方形，一个是正方形。然后你现在的做法是，我积分都是对着方 方程做积分。Okay, in this case, they are changing the irregular area of element, which is quadrilateral trapezoidal, to integration with the square area. This square area has a unit of eta and zeta that change from 0 to 1 respectively in their two orthogonal axes. Okay? With this, now we're going to re-express, because del u, del eta or del u, del zeta, they are Jacobian times the strain in the x and y coordinate. What we really need is the strain in the absolute coordinate. Okay? But then they can be expressed in their map coordinate in this expression. Okay? This map coordinate is good for you to do integration because it is a square equation that's very direct. Okay? The inverse of this Jacobian will give you the expression here. Okay? And these expressions, you will now go to do the substitution into w del x, w del y, or w del y plus w del x. You're going to have the expression here. Okay? They look complex, but they are identical to what you did. Okay? At the moment, you do view the benefit for triangular angle, because triangular angle is a linear, is a concentric element. Every displacement chain is linear. Okay, so they are identical to what you did by space coordinate. But this will become handy when you are handling quadrilateral element. Okay, you can see here my strain energy, which was expressed as the complex term integral over the space of the area dx d1. But now you can re-express them in terms of the new coordinate. There is a determinant of the Jacobian, and then the eta and the zeta. Okay? So this integral previously was the integration over the area, but now the integration will be a simple number between 0 and 1. Okay? 所以这个 isometric parametric formulation 的最重要的一个点就是说，你原本是要对面积积分的，但是我现在是把它用这个坐标转换，你的是转换成一个方形的这个坐标，它的这个单位变化基本上是沿着一个坐标从0到1，然后另外一个正交的坐标的也是0到1，但是你要乘上一个Jacobian。Jacobian 就是一个面积变换的一个比例。In a way, you think that Jacobian, the minimum of the Jacobian is a matrix, is an area. Okay, in that way, so you're going to obtain the same expressions. So far, you don't need to use this, but in the quadrilateral element, square matrix, then you'll find that handy. Okay, so. Let's see, let me show you quadrilateral element. Let's see if you can see that. Okay, now you're going to see that if you enter the rectangular element, okay, the interpolation of that is going to be different. Okay, so in this case, the definition of the rectangular element will have origin at the center. Okay? You're going to have the v halfway for b, from minus b to b. You're going to have the height from minus h to positive h. So this is the element we define. And then your interpolation of the displacement is no more linear. Why is no more linear? Because you're going to have a bilinear interpolation. In the case of bilinear interpolation, what are you going to have? You're going to have xy term. Okay, previously you have x term, you have y term, but now you have xy term in the interpolation function. So by counting the number of coefficients, you have now 1, 2, 3, 4. 4 coefficients for the interpolation function. I think that's fair because you now have 4 nodes. Okay? By substituting the coordinate, not 1, not 2, not 3, and not 4, into the interpolation function of the displacement. Okay? So I'll take the first quadrant, second quadrant, third, and fourth, and then you're going to have the expression here. Okay? Substituting all the coordinate into the interpolation function. Now you have where you determine the other coefficient and all the 1 and 2 and 3. Okay? And now, how to solve for that? You solve it by Cramer's rule. You can find A naught. A naught has a unit of displacement. Okay? It's a sum of 4 horizontal displacements divided by 4. Okay? And then next, how about this other element? How about A1? Yeah, A1 has a unit of displacement over the width. Okay? And that displacement is the difference. Okay? And how about A2? A2 is also difference of displacement divided by height. Okay? Height. And then how about A3? A3 because it's a quadratic function. Multiplying xy, there's a unit of displacement over the area. Okay? And now you obtain your A0, A1, A2, A3 in terms of U1, U2, U3, U4. The maximum matrix is expressed in the left hand side. Okay, so now what you will do? By multiplying it back to x and y, okay? You have 1x, 1 times A0, x times A1, y times A2, xy times A3. Then you're going to have the expression like this, okay? This expression already has a grouping using displacement 1, displacement 2, displacement 3, and displacement 4. And their pre-multiplier is what you call bilinear interpolation function. Okay, how do you do the grouping? If you look carefully, the shape function 1 is x minus b times y minus h. Okay? The shape function 2 is x minus b plus y plus h. And then the shape function 3 is x plus b times y plus h. Shape function 4 is x plus b times y minus h. Okay, how do you see this? Okay? How do you see this shape function? Okay? This is what we call bilinear function. Okay? It's very easy to see. Why is that? Take this coordinate. Take any x minus this coordinate. Okay? So if you want it to be, want this to be 1, okay, on the left hand side. Now we have a very simple way of remembering this shape function. If you have a square, your origin 0, your 1 is minus b minus h. This is minus plus b minus h. This is plus b plus h. Minus b h. This is in the x direction. This is in the y direction. If you want the shape function to be 1, okay? Take for example, if you want this point to be 1, and other points are all 0, okay? Along the side, you see this. Along the side, you see that, okay? So this is now what kind of the shape. At the center it is R, okay? But the shape is the shape of pyramid. Okay? 那你要怎样找出这样的形状函数？又要 b 它是 e 呢？ So one way of taking this is take this coordinate and then this coordinate minus the coordinate, okay, and this coordinate, okay, minus this local coordinate. Yep. And divided by 4, they are going to be 1. 看到没有？你如果这个位置是负 b 负 h， 你直接 x 减掉 b，y 减掉 h， 相乘，然后除以4，这个是负 b 负2个 b， 负 h， 负2个 h， 除以4。How do you find the shape function? You force it to be 0. So this is at minus b minus h. The expression is x minus b times y minus h divided by 4bh. Then you have the shape function 1. Okay. How about another coordinate? This coordinate is plus b minus h. The shape function is going to be minus x plus b times 1 minus h, then that's your shape function. How about the other point? Continue the case. Okay. Yeah. So you can go back and look at that. The main idea is by doing this kind of shape function, okay? Yeah, you can do as you did in x and y coordinate. Okay? Find the strength in the x direction. Okay? To do the partial derivative. You find the strength in the y direction. Do partial derivative of the shape function. And then you can do so to find the shear strength. And in short, you have this expression all in terms of absolute coordinate. We are still not using any mapping. Okay? Multiplying the B matrix with the D matrix, you're going to have the stress. And then if you do the substitution of the expression above, then you're going to obtain the stiffness matrix. Okay, but this thing is very complex. Why is that complex? You now need to do the integration of B, D, B with respect to the coordinate x and y. 所以这个式子为什么会难？难在它的积分的函数，它是属于空间变化。So in this case, if you want to do that integration, your expression is going to be complicated because your every coefficient is a function of coordinate. Okay? Then that will